Select the correct answer. What are the domain and range of this function? So to make this problem, you could graph it and identify the domain and range, and that absolutely will work. But let's use our general knowledge of what the basic shape of logarithm graphs look like. Typically, logarithm graphs are going to look something like this. They may be somewhere else in the coordinate plane. They may even be reflected a little bit, but the point is all logarithm graphs, pick a different color, will have a vertical asymptote. So they'll all have a vertical asymptote. When we're finding the domain and range, that's key, is figuring out where that vertical asymptote is. What is true about all logarithm graphs? Well, they have a vertical asymptote, not a horizontal asymptote. So do all of these graphs go up and down forever? They absolutely do. Like, it's pretty clear that this graph goes down forever. And if we extend this out, it's moving to the right, but it's also going up infinitely. So the range for all logarithm graphs is going to be all real numbers, or negative infinity to positive infinity. So if nothing else, memorizing that little fact, you're giving yourself a 50-50 shot. The domain has to do with where does the asymptote exist? And remember, the asymptote, by definition, this is going to be a really short, abbreviated definition, means where the graph does not exist. Sometimes they write DNE for does not exist. So we have to figure out where this graph does not exist, or where this graph is undefined. Well, we can do this pretty easily just by thinking about this problem logically. Doesn't really matter what the base is. Can you take the logarithm of, let's just call this base 2, and let's check this one. So this is saying the asymptote is at 1. So the graph only exists everywhere from 1 and to the right. So if we substitute 1 there for x, what this problem is saying 2 to the what power equals 1. Sometimes this trips people up, but is that possible? Can you raise 2 to a power and equal 1? Well, yeah. 2 to the 0 power. Anything raised to the 0 power is 1. So this graph does exist at positive 1. So that's probably not the correct answer. Okay, well, let's check the other one. Let's check 0. So let's take log base 2. We're taking this. Log base 2, and we're replacing x this time with 0. So what power can you raise 2 to get 0? And you can't. You cannot raise 2 to a power and get 0 or any negative number. You can't. So it's not possible to raise 2 to a power to get 0 or any negative number. So anytime you're trying to take the log of 0 or a negative number, you know that's where the graph doesn't exist. So essentially what we've got here is we've got an asymptote. Let me pick a different color. It's going to be right here on the y-axis, because this graph does not exist anywhere where x equals 0, which corresponds to on the y-axis. And then the basic shape of this graph, like if we made a table of values, which we of course could, would be this. And you can see this graph, for the domain, this graph moves right infinitely, but it can't move to the left of this barrier line. It can't get past that 0. So the domain is 0 to infinity. The range is negative infinity to positive infinity.